Okay, so when we left off, we were looking at sort of where this had gotten us, and this is there's an older machine here running some older benchmarks, but this is still a pretty good model of what we've seen so far, right? This has all the bells and whistles that we've seen, and some that we haven't. We haven't gone over the memory systems on these machines yet. So here we have a machine that its peak IPC is 4, which means that similarly, its baseline CPI, the best that this machine can achieve in an ideal situation is a CPI of 0.25. It is a 4-wide machine. And you'll note it does not get there. On the other hand, you will note that for a number of these spec CPU benchmarks, it does get below 1. Right. So if you're looking at what the goal was to beat the Flynn limit and actually get IPC. Then in all these cases, it succeeds. In this case, it almost gets there. Right. Now, one of the things that you will find, the reasons that you get these very different performances across these different benchmarks is that they have very different bottlenecks. So multi-commodity flow is a large graph problem. I mean, large by the standards of the day, it's only a few hundred megs, it's not gigabytes, but it's large enough that it does not fit the on-chip resources, and you're chasing pointers all day long. There's no locality. We'll go on the memory system on Thursday, right? So you should expect this to be a bit on the slow side. This is mostly a memory issue. Similarly, A-star has some limitations. It's a search problem. GCC is an interesting one. GCC, well, what do you think the bottleneck is with GCC? Anyone want to guess? GCC is a compiler. Branchy, branch. Right? Conditions up, down, left, right, and center. Right? So, okay. Now, if you compare, right, you're looking at your dynamic out of order and your 2-wide in order, right? This is quite a bit better, right? But as we saw on Thursday, you're spending a lot of power and area to get it, right? So you want better performance, you can get it, but it's got a cost. Okay, now let's talk about why, even though we have had hardware branch prediction for decades, people are still writing papers about better branch predictors. This is that same Core i7 we saw here. Right. And let's take a look at, and this is a mid to high 90% accurate, broadly speaking. If you look at these numbers, right? This is a branch misprediction rate. You'll see that in only one of these benchmarks does it hit 10%. Right. And if you look at the amount of wasted work, right, these are wrong path fetched instructions. There's still a lot of them. Right, so there are lots of instructions that we have fetched that are not useful at all. Right, because remember, in order to get these higher IPCs, we need a big window of instructions we're actually going to execute. If we find parallelism in instructions we are not going to execute, that didn't help us much. Right. Now, there are actually a bunch of interesting interactions that happen here. This isn't just, as you can see, that they're not easily predicting how much wasted instructions you get as a function of what the branch misprediction was, right? Obviously, lower, there's some correlation, but they're not really immediately mapped. So one of the things here is that if you look at MCF, it's only got a 6% branch misprediction rate. But because you'll have a bunch of loads that are stalled. So a lot of these branches are fairly deep in the pipeline. You get a big window stalled behind some load that hasn't resolved yet. You can get a bunch of things that are speculated on top of speculated on top of speculated, none of which have actually got the right value to train everything with. And so you have to throw away very large windows of work. Some of these other cases, even though there are a lot of branches, right? If you're not really having difficulty clearing your issue queue, then the number of branches deep that you're speculating doesn't necessarily get that high, right? So again, the exponent on how many branches deep, right, versus the overall accuracy play around with the likelihood that you're actually fetching useful work or not. Okay. But I'll post a paper that we can look at. We're not going to read it in any depth, but you can just skim some of the pretty pictures from not too many years back, just a few years ago. Folks at Intel arguing that branch prediction is still really the challenge we should be working on. Right. This is a fundamental limiter on getting your logical instruction window wide enough to get useful ILP. Right. All the rest of the resources we could throw at making our machines wider are going to be useless if we can't get the right instructions in. Okay, that's where I was hoping to get to on Thursday. That sort of wraps up the Thursday mindset. Now let's switch gears briefly. So recall multi-threading. So fine-grained multi-threading, as we saw, was a fairly natural bolt-on to in-order microprocessors. So in your in-order microprocessor, you're trying to avoid all of your instructions getting stuck behind some pipeline visible dependence. Now, in an out-of-order processor, yes, well, your ROB or your IQ could fill up. You've already got structures to help you with that. Right? This is not you're not worried about, a 6-cycle, delay, ruining your entire weekend. Right? It's not going to be a problem. You got a pipeline stall between two dependent instructions. That's fine. I'll just keep executing past it, find more stuff to do. But as we saw in those graphs, we weren't really hitting, that 4 mark very often. Right? We were not frequently hitting the full utilization of our machine. So, is there a corresponding leading question? The answer is, of course, yes. Is there a corresponding natural bolt-on to do multi-threading for a different purpose in out-of-order computation than in an in-order processor? And that'll be simultaneous multi-threading. Okay, so simultaneous multi-threading is going to very tightly integrate with mechanisms that we just built. Right, it's going to piggyback on top of the things that we already have in our out-of-order machine. It would not be a natural extension to our in-order models at all because it requires a bunch of things that aren't there, like renaming. Side note, the International Symposium on Computer Architecture, arguably the premier conference in computer architecture. Some people in micro might disagree, but mostly it's pretty clear. Gives out a test of time award, right, for the paper with the most impact from 15 years prior. And, in 2010 and 2011, they gave out in consecutive years test of time awards to 2 papers on simultaneous multi-threading from 1995 and 1996, right? So the papers are coming out in the mid-90s. You could go buy them under the branding of hyperthreading from Intel by 2003. Right, so about a 7-year lead time, but a lot of impact. Okay, so here was our original execution. You get some delays, they call everything up. So fill in your wasted vertical space with work from other threads. We want to do even better. We want to attack this horizontal space. We want to find other work to do in a particular cycle. Right? So how are we going to do that? Well, here's the fun thing, right? In our FGMT setup, we had to sort of keep all of our instructions from different threads separated because otherwise it wasn't really clear, which register T0 you were talking about, and other sorts of similar ordering and other issues. But we already have a mechanism that will allow you to virtualize the resources. So let me ask you the following question. I have an add instruction from thread 0. I have an add instruction from thread 1. I have renamed both of them to be referring to physical registers. Is there going to be any problem if I send them down the pipe at the same time? No, because I mapped them all both entirely into the same space of physical resources that I'm using. That same identical, without any changes at all. Yeah, okay, maybe there's some scheduling policy reasons that you might want to change your age-based distribution to know which thread the oldest instructions are from, but fairness and optimality aside, but with the same hardware you could. That was the second paper. First paper, how do I SMT? Second paper, how do I SMT well? Right. So that issue queue logic is still going to be the same as it was before. Right. So if I've renamed everything into this physical resource space, I can freely intermix in a single cycle any of the instructions that are ready from some number of different threads. Now, is it going to be free? No, nothing is free. But is it going to be a fairly natural exploitation of some mechanisms that are already there? Yeah. Okay. So again, you may be more familiar with the brand naming on this from Intel of hyperthreading. It's just brand naming. SMT is an older term. If you happen to spend too much time in the vicinity of Austin, Texas, you'll be told that SMT is really, really nothing new, and the CDC 6600 was doing it, but certainly modern SMT has its birthplace in the 1990s. Okay. So if you excuse me. If you look at the history of a lot of the SMT offerings, with a few exceptions, and we can go further, but roughly about 2 to 1, right? So you usually want to support about as many threads as your issue width divided by 2, and that really boils back down to, if you look here, right? An argument about, on average, how much do I think I can exploit per thread, right? So you're making some utilization arguments, right? Now, obviously, if I were to put 2 of these together, only this guy is actually, more than half underutilized. So there's going to be some resource contention, but it's a reasonable rule of thumb from a provisioning perspective. Okay. Now, there are, it turns out, a lot of can do this. We'll walk over some of the design choices. Some things you have to do, some things, well, up to you how you want to play it. Okay. So as with FTMT, as with sort of any flavor of multi-threading, some things you just need its own, right? Every thread has to have its own PC. No PC, no sequencer. We are going to need separate map tables. I do need to know which thread, physical register 23 actually belongs to. I am not randomly, assigning things back to different folks, and they do have their own architectural register files. So i.e. the set of things which are externally visible about the state of the thread, right, have to be duplicated, right? I need to actually keep track of these things. Okay, as before, things that are stateless, like an ALU, dynamically share them. And then everything else, we have some choice. Okay, so for TLBs, we'll need potentially some additional metadata. So this something we haven't talked about too much because the order of these lectures, we haven't gone through the memory virtualization system. But suffice it to say, I need to know which memory space I'm referring to. My address 400 million, your address 400 million. If I'm sharing my TLB, I do need to figure out which address space you were coming from. Things like the return address stack are not terribly useful to share, right? Again, it's a predictive structure. I could share it. It would be a bad idea, but I could. There's no correctness issue. This is a performance question. Right. Similarly, branch prediction tables, whether you want to share those are, again, a function, or whether you want to give some degree of, because you can also have choices that are neither hard nor soft partitioning, right? So you can have some degree of hard partitioning to have minimum resource allocation, prevent starvation, right? There are lots and lots of policy spaces here, right? Design space is large. If they're running the same code, right? So if you're SMTing across multiple copies of the same parallelized program, or multiple instances of the same process the same program implemented as a multi-threaded program, then you're going to learn a lot of the same structures. That's good. It turns out in practice, you're often better off with SMT running multiple different processes with different behaviors, right? You can ponder why that might be a good idea in a second, right? If I have a finite amount of resources and different programs have different bottlenecks, then probably ideally I would schedule things in a heterogeneous fashion, right? So that I don't put two things with the same bottleneck on the same core, right? But so often these are actually for different structures. So you're probably going to want to try to deal with the fact you get some aliasing and noise in BHGs and BTPs. Okay, caches already dynamically shared, so no big deal. Okay, so let's modify our existing processor to do simultaneous multi-threading. Okay. And so you can see that it's not necessarily radically modified. So I'm going to need a thread scheduler so that I'm fetching from different sets of instructions. Now, in any one cycle, I'm only going to be fetching from one thread or the other, right? So I'm not going to be trying to get multiple instructions from multiple threads in through fetch at the same time. It's really, really not worth it. I've already got all this decoupling on my front end anyway. It's going to queue these things up and introduce them over to here, which is where all the actual magic happens. And actually supporting my memory, 2x the memory bandwidth to fetch from two threads at once is just not worth it. Again, remember that the whole point of this, if I could fully utilize this machine with one thread, I'd already do that. So I can't fully utilize the machine with one thread. So doubling my bandwidth is a big ask. Right? Okay. So I'm going to fetch things. I'm going to decode them. These are basically stateless in any reasonable ISA. Now here, we're going to actually have to figure out which thread you came from. Right? But again, we're still doing, in any given cycle, threads. These instructions are coming from one thread or another. So that's pretty easy to keep track of. And we're just going to alternate between which of these map tables we're looking up in. The free list is shared, right? The set of physical registers is a set of physical registers is a set of physical registers. Right. Now, the semantics here on the ROB, on the LSQ, we'll talk about in a second. These obviously partitioned similarly with the PC as part of the thread state. So how do I want to share the ROB? This is as much an implementation question as a logic question. So the way that you build the ROB practically does not lend itself to entry-level granularity in partitioning among n threads. Right? The way that you want to build this as a practical queue memory structure with reasonable access time and area overheads means that I'm better off either hard partitioning it or having fairly coarse-grained chunks that I allocate and deallocate at a relatively infrequent point in time among multiple threads. Right, so you can do some dynamic partition here, but this is not going to be at the entry level. It just doesn't make any sense to do all of the routing, swizzling, muxing, et cetera, for every ROB entry to figure out, well, in what order among all the threads do I have to sort of logically connect these together to get the total order of the structure. Remember, it's an ordered structure, right? So I can't just sort of arbitrarily and delete resources. LSQ also ordered has not quite exactly the same partitioning problem. Similar to the ROB in that it's not going to be arbitrarily divisible. But the deeper question here is in the LSQ, the order operations that I'm doing here now really do need to be local to, right? The checks that I'm doing for address resolution do need to be local to my particular thread sequence. I don't care about whether my load is older or younger than your store, right? So I do need to actually cut this off and make sure I'm not looking at another thread's resources. So again, the granularity at which you do that can be a bit coarse, but you're going to chop this into pieces and split this, right? You want it to at least be logically partitioned, however much dynamism you do or do not support in terms of how many of these partitions you allocate to a particular thread. Right? So in the simplest case, they're just two partitions and each gets one. Right? But even with two threads, I might have 4 partitions and you can go between 1 to 3. Okay. Right. The pipeline latches, same as before. We do need to keep track of a little bit extra metadata, but everything else is pretty straightforward. Now, if you look at how you want to size some of these structures, in practice, when we move to a SMT model, there's an expectation that you will get more mileage out of being able to populate a larger issue queue, right? That there might be more exploitable parallelism within window. That's worthwhile to build. And at the ROB level, given where we have traditionally been looking for that parallelism, if I just imagine that I've just cut all the resources in half, I've given you now a situation where in the case where only one thread is scheduled or the other thread is otherwise idle, you have at most half the window to look for to exploit your parallelism. So generally, we want to actually make these the total amount of resources larger than they were in the pre-SMT machine, right? Given that we're now going to have increased residency of users of these resources, right? Because what we want to do is not dampen the single-threaded performance in the case when there is no co-runner, right? So my goal should be for my SMT machine, when I am only running one thread, right, that my performance will not be substantially reduced, right? So just some marginal stuff at the edge. Okay. Now, if I'm running 2 threads on my SMT machine, do I expect the performance that I had for that original thread to be the same as it was when it was running by itself? Once again, ask the question, what performance metric is SMT designed to optimize? Well, as with all forms of multi-threading, yeah, throughput, right? So it's not trying to reduce single thread latency. That's just not its job. It's a utilization improvement. It's a throughput improvement. So the expectation should be that there's probably going to be, with more things demanding resources, some negative impact on single thread performance when multiple threads are scheduled. Right? So you want to have this dynamism. When I have the core all to myself, I should maximize the amount of resources that I can use. Again, if your issue logic doesn't care where the instructions came from in terms of threads, right? My peak issue is still the same, right? So my reductions in performance from single thread are all going to come from whether or not I was even able to expose a big enough window, right? So if the way that I partition some of these structures means that instead of having a 256 entry ROB, I have an effectively 128 entry ROB, then I'm going to lose a little bit, but that's small compared to having 4 issue or 2 issue. If I go down to 2 issue all the time, I'm definitely losing a lot of performance whenever I do actually have more parallelism exploitable. Okay. Now, what should our expectations be with respect to the single thread slowdown compared to FGMT? right? So remember in FGMT, you got some fairly ridiculous things up there like the dental core HEP, i.e. create XMT, where you were 128 threads deep, right? So you didn't even have caches. You just were trying to hide main memory latencies before you scheduled another instruction. Obviously, your per thread CPI there was terrible, right? So how much of a slowdown should we expect for SMT? What's the key way to understand where the slowdown is going to come from? All right, so in FGMT, I am time slicing your access to resources. Am I doing that here? Not really. I'm time slicing a bit on the fetch side, right? But as long as I can sustain a rate of instructions coming in that's greater than the at least as high as the CPI I could have gotten before, right? Again, we were trying to fill up these big windows. We got big buffers and queues. I can worry about the average there, right? I get averaging. Right? I'm not worried about the fine grain. So am I time slicing? Am I preventing you from doing work in any given cycle? What are the situations under which in SMT, right, a bunch of threads in, I rename them all, they're all in the issue queue together. What are the reasons that one of my instructions doesn't execute? What are the reasons I get no work done this cycle? Compare, contrast, FGMT, SMT. I know, that requires you remembering FGMT. It's already been purged from your mind. That was in the previous midterm. So in FGMT, I can only issue threads from this, issue instructions from a particular thread in the cycle. Here, everything's in the IQ together. So if your inputs are ready, no matter what thread you are from, right, you could go. Right? It might be that there are a bunch of older instructions from other threads and it prioritizes someone else in front of you. Right? There is contention. If there is more work that could be done than your machine can sustain this cycle, you will be delayed. Right? But if there are 2 instructions from you and 2 instructions from somebody else, you both get to go together. Right? So the chief thing that is going to reduce your performance here is just whether the machine is in any given cycle or run of cycles overloaded. If I have more available work to do than I can clear from that queue, the queue will back up, right? But this is all about averages and rates. It's not about you go, you go, you go, you go. It's a terrible car. I know. Okay. So SMT in practice, good rule of thumb. If you're scheduling 2 threads, expect maybe a 25% slowdown. Right? It's a reasonable rule of thumb. It depends a lot. Are they memory bound? Are they compute bound? Right? Do they have the same bottleneck? Do they have different bottlenecks? Do they cause cache interference where it goes from my working set fully fits to neither of our working set fits? So lots of nasty things can happen. But if you want a simple averaging rule of thumb, right? About 25% slowdown. For scheduling 2 threads, and scales fairly reasonably to 4. Whereas with FGMT, it's usually going to be quite a bit larger than that. Right? Again, in your worst case, you're looking at something that is roughly linear in terms of the overhead. Right? So if you're only scheduled once every n cycles, right, your slowdown can get real bad real fast. Okay. So the initial implementation of hyperthreading wasn't super aggressive. It had a lot of static partitioning. Right. So if you look at a 2003 era Pentium 4, 2-threaded, right, then they just carved it up into 2 chunks and then made each of them a bit bigger. Right. Now, the interesting thing is that it was reconfigurable technically, just not dynamically. This was a BIOS level boot time configuration option to either have T equal to 1 or T equal to 2. We can either have one thread with twice the resources for your RB and your LSQ, but you lose your hyperthreading, or you set it to 2 and you get two-way hyperthreading. Subsequent designs have been a bit more dynamic, especially the higher thread count designs from things like IBM. The IBM Power series, get things like a 10-way multi-threading. Right? But again, they're targeting very different workloads. Right? Okay. So, good news, no starvation. Bad news, if you do dynamic partitioning badly, you can get all sorts of problems. So I mentioned that that second Test of Time award-winning paper. It turns out that a relatively simple policy measuring a very easy to measure metric can help avoid some of the worst pathologies in thread scheduling. Right. So if you think through it for a second, if I've got multiple threads in my machine, right? Think about all these queues. I'm sharing these queues. I got one thread that is making lots of progress. Right? So instructions go in, instructions go out. Instructions go in, instructions go out. Instructions go in, instructions go out. It is actually not particularly resident in a lot of these queues. Right? So I'm clearing my queues about as quickly as I'm filling them in. I'm not occupying much of the queue. Right? I got some other thread. It's making no progress. I did a load. It went all the way out to memory. Got a bunch of instructions behind it. I got some other load. It went out to memory too, pointer to whatever. Right? Eventually, the thread that is making no progress will consume all of your resources if you let it. Right? Because the reason it's consuming more and more ROB and IQ resources, and that they're staying there and not leaving, is because it is not able to effectively utilize them. Right? So it turns out that if you basically give priority to the things with lower utilization of the structures, right, and ensure that they actually can continue to go forward at the expense of the things that actually are grabbing a lot of resources, you get actually some pretty reasonable results with a very simple metric: avoid starvation. So the I count thread scheduler, very simple, works well. Okay, in practice, a little bit bigger. So if you want to evaluate does multi-threading do anything, you do need either multi-threaded or multi-process workloads. So here's a different set of benchmarks. These are the Parsec benchmarks. Came out in 2008. That was Parsec 3.0. Well, these are all from Parsec 3.0. 3 or 2? Yeah, 2008, 2006, 2008. And these are a set of multi-threaded parallelized benchmarks. They're all parallelized in a fairly straightforward fashion, which is to say that the work being done by all of the threads, all the threads are executing essentially the same code. They may have load imbalance, but it's not a heterogeneous task parallel or other sort of pipeline sort of parallelism. This is parallel parallelism, right? So lots of threads, fork and join, fork and join, fork and join. And so good news, right? So speed up in this respect is effectively a throughput measure, right? Throughput aligned measure. So it's the latency of more unit tasks across these threads. So for most of these, it was a good idea, right? You can also look at this from an energy efficiency perspective. We haven't really talked too much about the particulars of energy efficiency. We'll get to that quite a bit later in the semester. But usually reasonably an improvement there as well. Again, this will align at least to some degree with the utilization of the machine. Right? If I'm already lighting up my whole IQ to search for new instructions to do every time, the more of them that actually get done, the more that the energy was put to good use. Okay. But not universally better. Right? So some of these things, I do build some larger structures. If I don't get a lot of benefit from them, doesn't necessarily pay off, right? And again, if I wanted to look at the single thread impact, right, it is actually going to be a slowdown, right? So again, the other way of looking at this is I had 2 threads. I did not get a 2x speed up, right? My utilization did not go up by 2x with 2 threads. But again, that matches, right? Look back to what we saw on that set of spec benchmarks. While more than half the benchmarks were underutilized, right, to some degree, right? Or actually, all the benchmarks were underutilized. None of them were hitting 4 wide. The degree to which you could expect to put twice as much work on there varied benchmark to benchmark. Okay. Now, the other thing you might be thinking, and again, you got to put on your right mindset, right? So again, these papers were coming out in 1995, 1996. You know what we didn't really have in 1995 and 1996? That all of you have spent almost certainly your entire life that you can remember having. What did we not have? And there are a lot of things we didn't have in 1995. So, but specific to processors, what did we not have in 1995 and 1996? You did not have multi-core. The first recognizable, I mean, certainly there were SMPs, there were lots of things that used multiple sockets, et cetera. The first recognizable prototype of something that looked like a modern multi-core would have been the proposal for Hydra coming out of Stanford in 1996, right? So you certainly couldn't go out and buy one. It was still a research topic. Yeah, but you're looking for when you went to multiple cores on a single chip, you're still looking at 2002, I think. Yeah. Yeah, and even there, those were well, in its infancy. So, but now that we're looking at right, this from the perspective of having enough resources to stamp out lots of cores, do we still want multi-threading, right? So again, this was a fairly modest set of changes to an out-of-order core, right? So your return on investment is pretty high, right? Take an out-of-order core, it's already got all these structures, and I'm going to give it an opportunity to find more independent work to do by just being able to feed those entry queues from multiple input flows, right? I've already got basically an identical, almost unchanged middle of my processor that's already doing all the heavy lifting. I don't have to redesign it. I don't have to give it entirely radically new resources. Yeah, there's a little partitioning fudge, but right. I just need to find more sources of work to do, and it'll exploit them all. SMT is a means of turning TLP into ILP. Right? That is the way that you should think about it. SMT is an ILP engine, and it finds a way to find more ILP from TLP. Right? Okay. What do you want to do? I mean, both will help. Right? More cores, good. More threads per core, also good. And the answer, of course, is that you don't, don't actually have to choose. Right? So everything that, well, not everything, because they kind of went to for a variety of of mildly interesting reasons. It's a non-monotonic progress with whether SMT has been supported. That had a lot more to do with which sort of branch of the lineage of processors Intel jumped back to, and they need to get more power efficient. But there's a reason SMT is around and is gonna stick around. It's really that underutilization. So pretty much everything that you're going to be looking at today has both. Yes. Okay. Yeah, well, it's gonna be uniform number of threads per core, unless you are having a heterogeneous core allocation. So you can imagine a model where, right? So let me give you a simple example. So imagine I have something similar to Intel's performance and efficiency core split, right? Where I decided, okay, yeah, what I'm going to do is I'm going to have some really, really beefy, heavily aggressive out-of-order cores to do my serial intensive, ILP intensive tasks. and maybe I put 4 of those, maybe 4 threads each, and then I've got some large number of really simple lightweight cores that I do for my very, very thread parallel tasks. Right? Maybe I don't even bother with SMT for them. If they're all just going to be running, highly, highly parallel, pointer chasing code or something, maybe I don't care. I spend all my budget on, maybe I'm going to make them in order, right? Maybe just have 64 in order cores in some array, right? Not how they've designed it, right? They're targeting some different workload balances. But there's certainly a lot of places that have been designed and explored in research for heavily asymmetric use in that regard. Yes.
Is it necessary that cores are like, cores a little bit more?
Yeah. So if adding another thread to a core versus adding another entire core, I will get more throughput out of adding another entire core. I also have spent a lot more transistors, right? So if we jump back for a second here, right? So changing the number of partitions in my LSQ and ROB, changing the number of map tables, small. Changing the number of register files. In an in-order core, the register file is a non-trivial chunk of the whole size. In an out-of-order core, it's not. This is huge, right? This is a big, expensive piece of logic. There's a whole bunch of other stuff going on here. So, going from 2 threads to 4 threads is a relatively modest total area increase of this core, depending on how much I want to over-provision my ROB IQ and LSQ, right? Whereas building an entire another core is clearly 2x, right? Yeah, and indeed, if you look at some different, depending on what your needs are, what you're willing to tolerate in terms of interference, or maybe you're a cloud provider and you're saying, look, everything is about reliability and SLAs. I might even just disable the hyperthreading. I don't want difficult to predict interference patterns. I want to tell you on this core and you on this other core, and never the twain shall meet. And your resources are hard partitioned, and maybe I don't even want multiple users on one machine for security purposes. There are lots of reasons, right, where you might want to build different points in this space. But if you're looking at the marginal return on transistor investment, then, at least for, modest numbers of, again, here's the if I already have an aggressive out of order core, right? If I've only got a 2 wide out of order core that's, pretty lean with relatively small IQ and ROB structures, like maybe I've got like a 16 entry IQ. I don't want to SMT that, right? That's clearly not the right design point. That's like a design point for an out of order core for a phone, right? And you'll note that those are in fact not, last I checked, SMT. But if I've got a 48, 64 entry IQ, I've got hundreds of entries in my ROB. Yeah, I'm not able to fully utilize, right, these resources. Go back several slides. Well, I'm doing the slide deck now. I got to remember. So this is even before this deck, where we looked at this as a growth in superscalar, and 2020 Zen 4 with peak ideal issue of 10, lots of asterisks, but right, but you're not hitting an IPC of anywhere near 10, right? So having SMT allows you to play better around with both. When you do have high periods, you can exploit them, but your average being much lower, other people can come in and dynamically slot in, use the resources as necessary, get better utilization of the machine. So good return on investment. Additional cores, still very useful, right? So in particular, actually, let me go over one other thing. This will become clearer when we, switch to the next set of slide decks. There's a very, very important piece of the system that's missing here that would be attached. Well, it's not missing, but it's not drawn to scale. This is, of the same sort of, this is a non-trivial fraction of the entire size of the rest of this drawing, if you actually want to put these to scale, right? And the sharing of the D cache is a fundamental limitation in the SMT model, right? So building more cores, your biggest return on investment might be that they each get their own chunk of cache to play with. And so you can work with larger working sets and actually get them to fit, right? They get their own L1. They also usually get their own L2, right? So there's some very practical things in the memory subsystem where sharing is not necessarily friendly. Okay. Where were we? Sorry for the back and forth there. Okay, so the answer is do both. Pretty much everything anybody today is going to do both. But they're going to be, as I've been alluding to, and we'll come back to, both when we talk about the memory system particulars and when we look at the parallel computing portions later after that. They're going to be better for different sorts of things. Let's skip over that. Okay. So let's talk about the tool that a little bit that we're going to be using. Good time. Okay. We got half an hour. So for project 3, right? The final project in this class, and you will actually be using this before then. You're going to be running some experiments. You're basically going to be building a layer on top of a simulator, right? And you can in fact think about projects 1 and project 2 as very shallow dives into what it would be like to build portions of a simulator. We're not asking you to build a simulator in this class; it's too much, right? But you'll be using Simple Scalar, and Simple Scalar does not model SMT, so you can stop with your Thursday notion of where we are in terms of what it models. But it is a highly parameterizable single core out of order execution modeling piece of software coming out of the early to mid 90s out of the University of Wisconsin. And you get some nomenclature out of the way first. So for a variety of reasons, it doesn't have a separated ROB and IQ. It's all just part of the RUU. But all the things that we've talked about, all those functionalities are in fact in there in the RUU unit. If you want to go and poke around in the manuals for Simple Scalar, which I believe should be linked up in the modules for this class. Does anyone bother to go read those? No? Okay. I didn't ask you to. There's no reason for you to. But some people just aggressively read things, right? So, okay. So it's got your RUU and LSQ. The only partitioning it has is Loadstore Q and the RUU. So again, all the ROB and IQ stuff, all there together. As per the original 1987 paper from Gracie. Right. It's got Loadstore forwarding, but the thing that you will find when you start playing with it is, as I keep alluding to, that there are a lot of options. Right. So we spent all of 331 trying to figure out how to build one processor. And in this class, hopefully you've already realized that there are a myriad of ways you could build perfectly reasonable processors that do not radically differ from each other in overall outcomes, right? That this design space has large numbers of local minima, right? Highly non-convex, right? So this was a tool that people built to help explore what type of processors should we even be considered building. What do the relative marginal trade-offs look like for different design choices? How do they play around with multiple workloads? Because again, right, I'm not going to just go spend $1 billion and fab something every time that I think I have an interesting idea, right? I want to actually get some data first that tells me it might even be worthwhile. Right. Okay. So how does this all work? So, well, it's got its in order parts, set of order parts, and its in order commit. And these should look fairly familiar. Fetch, decode, rename, dispatch. Sort of smush all those together. Issue and execute together. Write back, will commit. Now, it is a more complicated model than we've done in that, different instructions can actually take different amounts of time. The functional units are modeled in a more asymmetrically allocated proportion. right? The banking within the memory system is actually modeled, right? More details are modeled. But at the high level, same sort of thing that we've been doing here, right? And the outermost loop, right, of this, and most simulators, right, is basically for every cycle, right? The outermost loop is not for every instruction. The outermost loop is for every cycle, right? We are modeling the progression of a system over time. I have a system, so it's basically a big finite machine. I poke it, it moves to a new state. I poke it, it moves to a new state. I poke it, it moves to a new state. All right, that is how the simulation basically has to work. If you're asking, how do you do this when you want to do, an aggressive out of order multi-core across multiple, like a Gem 5 level, you're looking for what we're using today, right? A more modern simulator would be Gem 5. I'm not even going to ask you to try to compile Gem 5. Gem 5 is a fun piece of software. The reason we're using simple scalar is in the first part of the name. Then you move to what we would call an event-based simulation, which is the same thing, except that we skip over all the cycles where nothing happens. Right. So if you assume sparsity, you can change your model, but still effectively you're iterating over time. Right. You can just skip to the next event that's actually going to occur, where between that. So timing simulation, fun stuff. Not gonna worry about it too much, but right. This is gonna do the same sort of thing that you're doing now, because I'll tell you about some of the hacks that are going on here, because they're relevant to your project. One, so if you look at the outer loop, and the code for simple scalar is available, you can go download it if you want. Right, non-commercial use license, free. It just sort of runs these backwards. It starts here and then moves backwards, because the trick that it plays out is it cheats on branch prediction. So it doesn't actually have this is actually effectively a mostly feed-forward pipeline. It really doesn't have these backward loops. So while it will model the effect of fetching all these wrong path instructions, it actually knows which way the branch went as soon as it actually runs through the initial instructions. It actually basically pulls in instructions, computes them in order, figures out what the actual values would have been from a value perspective, and decouples the actual program flows from the timing model. Right, so all of this is actually built as a timing model rather than an execution driven flow. Yes. No. These are functions that are in simple scalar. Right, so if you want to go look at simple scalar, right, the REU commit is handling commit. REU write back is handling write back. Issue is issue. LSQ refresh handles the ordering within the LSQ. Dispatch handles all of this. Right, so they smush multiple stages together there, but it's all in order together. So there's some games that they play, and you can imagine that if I had a purely feed forward, even this isn't purely feed forward. There are really sort of two ways that I can simulate a pipeline, and they chose the less extensible way, but it's fast, right? So if this is purely feed forward, data just flows this way. There are no feedback loops, right? Spherical cows, modularly filled with milk, yada yada. Then I can basically compute the function here, knowing that it depends only on this. Then compute the function here, which updates this, but I've already read it, so I don't need to worry about it. As long as I walk backwards, right, this all works, and I don't accidentally read a value from over here in this stage, teleporting its way on through. Right? If I do them in the order that they're written, and I read this to update this, to read this to update this, to read this to update this, oh, suddenly I execute an instruction in one cycle across many pipeline stages. Right? That would be bad. The other way to do this, if you're looking from a modeling perspective, is think a little more how Verilog actually is doing this, where what you really need to do is explicitly acknowledge the existence of some input side to this that you are going to compute, right, versus the value that it currently has right now. right? So you need to double the set of sort of logical variables. Everything turns into a pair, right? So I have my current value and I have my next value. And then I can do these in any order, right? I can do these in any order within, again, this is a pure feed forward flow. Even when you start to introduce loops, you can do it in any data flow valid order. And you say, okay, look, I'm going to do some computation of this next value purely in terms of this value. Great. But I'm not going to actually update anything yet. Right? So you'd separate your computation into a set of updates of the next values, and then you'd have some equivalent of your always at pos edge clock. You basically have your clocking function that takes all the next values and sets them to the current values en masse at the same time. Right? So if you are ever interested in building something that isn't simple as a simulator, I strongly recommend you go with this model. For project 1, this is not required because we've by removing all the control instructions, everything is everything other than the return of registers to the free list is purely feed forward, right? So it's, but again, either of these will work. They have a little hack. But again, you can go look at their main loop. It goes, right? Because they made everything feed forward. Okay. Put it down over here. This is just describing what these do. You can set some of these parameters independently. So we don't have to set a total width for the entire machine. Right? We set a width for each of these individual stages. So you can investigate asymmetric front end, back ends to your pipeline. Right? You can set the latencies for all of these events. You can set some overfetch here to deal with the misalignment within the fetched aligned fetch block. Right? So you can set some sizing parameters independently, right? How big is your RUU? How big is your LSQ, right? How many instructions at most can come from each of these structures, right? Here are your allocations of functional units. So again, so far, we've been looking at the simplified version where I say it's 4 wide, and that means 4 of anything. Clearly, that's not really how you would actually build it. It just makes it simpler to describe on the piece of paper, right? So you can say how many floating point multipliers, how many floating point LUs, how many memory ports, how many integer multipliers, how many integer LUs, right? So you can look at how the provisioning of different resources, right, affects your ultimate performance, right? So again, this is a tool for design space exploration, right? Where we don't know what the best processor is going to be. And even to the degree that we have ideas about what the best processor are going to be, we need to go and validate it against other possible designs. Okay, this handles write back, data forwarding. This handles commit. Commit is in order. Thank you. Okay. Right. Okay. So time we have left. We got 15 minutes. Okay. So the first time you'll actually use simple scalar, I can't remember if I clicked the publish button or not. So let me flip over to Canvas for a second. Is actually with a little script that you'll be doing for your first writing assignment. Again, you don't have to do any of the settings initially. That will come in project 3. Published. Good question. Yeah. Okay. So you could have read this if you wanted to. Here we go. So let me take a look. Let me show you something again. You'll be sure, fine. Good enough. And okay. Again, you don't have to. You're not going to have to do anything interesting with this. But excuse me. So here's a little script that is going to do a very, very small targeted single feature design space to get you started with the idea of design space explorations. So in particular, as we did get to today with all that wasted fetch, branch prediction still kind of somewhat important. This is going to look at an array of different, oops, well, so be it. An array of different branch predictors that can be modeled within Simple Scalar. And so you're going to look at the relative impact of choices in branch prediction on both an in-order and an out-of-order machine. And then you're going to look at how you would try to extract the findings from running these simulations. They're only going to be like 60 simulations. It takes like 2 minutes, right? It'll probably take you as long to remember how to log on to our department machines as it will to actually run it once you're there. I strongly recommend not going through each of the output files line by line by hand and copying things into Excel. That is not the computer science way. grep is your friend, right? I will do a little video on this when I post the assignment. I haven't had quite as much time as I thought I would to get the writing assignment out, but it's breezy. Okay, so you can see these are all of the parameters that were needed to even define what it is that I'm simulating. You can see most of them are shared, but we have two. This is an in-order and this is an out-of-order machine here, and the issue lists are different. And here you can see some different branch predictors. So obviously perfect branch prediction when possible. So in general, it is always useful to have an understanding of how well you could have done, right? If I want to understand, am I doing a good job, right? And I say, well, am I doing a job? Well, what was my score? My score was 5. 5 good? Is 5 bad? I don't know. Was it 5 out of 100? Was it 5 out of 5? Was it? So perfect branch prediction, at least in this case, is something we can actually model. It is not always the case that we can model a fully idealized system. It may be ill-defined. Or it may be well-defined, but may be combinatorically difficult to figure out what the best settings would be in a lot of these design spaces. Branch prediction at least is easy. Not taken, we all know that one. So here's how to read this. Bimodal branch predictor, again, are a simple, nice one-level branch predictor. They always assume, they don't even ask you how many bits per FSM, it's always 2, right? So this just says, how big is my table? 2048 entry. Here are some 2-level branch predictors. If you don't remember 2-level branch predictors, that's okay. Part of the writing, the first writing assignment is to read the paper that introduced them. So you will understand, come now, notepad. Be not thou so unkind. Okay. Is to understand which of these 2-level branch predictors are, right? So these are, excuse me, these are fairly standard 2-level branch predictors where you have a history, and then based on the history, you're then going to do a lookup into some number of bimodal tables, right? You can see 2 different configurations there. So again, think about it this way, right? With the relatively similar budgets, there are many different configurations of branch predictor in allocating resources across either the first or second level of that branch predictor, right? They're not going to give you the same results, or they're not going to give you the same results across different benchmarks. And then finally, this is a tournament predictor. So I'll point you to the Simple Scalar manual to interpret exactly what sizings that is implying. But a tournament predictor is trying to figure out whether a branch is easy or difficult to predict. Right. So again, I don't need a 2-level branch predictor to tell me that for I equals 1 to 1,000,000, I should predict taken. Right. And a bimodal branch predictor is cheaper for prediction than a 2-level branch predictor. So if I can have a predictor, right, that tells me whose resources I should be bothering to trust and update for a given PC, right? Then I can make better use of the same hardware budget. Okay. Don't worry, we'll get reminders on all of these. This one you can just go read the particulars of how the turnover predictors is done within Simple Scalar. You can read in their manual. The rest of them, these two, you'll read in the assigned reading, which is posted but not assigned yet. Again, long story short, I need to make sure that I don't need to add any new fun keywords for ABET. Yay, ABET evaluation years. So I thought I was going to get that done by Friday, but you know, life happened. So you'll run this. It'll take about 2 minutes, and then again, I strongly recommend. Sorry. I strongly recommend using utilities to extract the data. You'll basically be pulling out like 2 lines per file for 60 files, and then you'll be plotting them. We're not going to require you to use Excel. You could use Google Sheets. You could use Ploticus. You could use GNU Plot. We don't care. But we will ask you to make some graphs. Graphing data is something that we do because we do comparisons in computer architecture. Right? So if there are lots and lots of different design points, we want to be able to examine them, try to understand trends. Because one of the other things that you're going to find out, if it wasn't sort of at least obviously repeatedly implied, the results coming out of Simple Scalar, if the name didn't already clue you, are not actual values you would get from actual processors. I can't trust the cycle count. It's not modeling enough, right? We've moved from spherical cows to cows defined only by convex hulls, right? Floating in a completely uniform fluid, right? If it's not better modeling, it's not actually accurate. But the nice thing about this sort of architectural simulation is it's very precise. You will get exactly the same results, wrong result, but you get the same wrong result every time you run. It's completely deterministic. And trend lines still tend to be highly indicative, right? So I will not trust that a particular cycle count for running any given benchmark. I will not trust that a particular optimization was exactly 10% better, right? What I will trust is if I have a baseline run with system A, and I have another run with system B, and across a broad suite of benchmarks, on average, everything went up, right? That if I can understand why it happened and match it to a physical phenomenon, that is probably a good optimization, right? So if you look at how these things actually play out, again, we're looking at the Simple Scalar version of this. If you're looking at what people are using today, they'd be using a system more like Gem 5. Again, I'm not pointing you at Gem 5 because it's hundreds of thousands of lines of code. I cannot succinctly describe the entire simulation loop in like 3 slides, right? And you might think, okay, well, fine, research simulator. No, actually, even in industry, if they're doing their internal initial studies, right? I work with people at AMD who are using Gem 5, right? So this is the unfortunate tool that we're all using for step 1. So you ask, well, does industry have better simulators? The answer is yes. But industry has better simulators of exactly the processor they're trying to build currently. They are not designed for wide parameter space searches. They're designed for very good modeling of a very narrow space that they're trying to fine tune, that they've already basically committed to lots of decisions, and they baked that into those the simulator. So sadly, we don't actually have any expectation that there's some hidden magical industrial tool that's just better, right? So I mentioned that these are going to run in like a couple minutes, and that's because we're only executing 2 million or 20 million, a few million instructions for each of these benchmarks, right? So the challenge you will find also in simulation more broadly is that simulators are slow. Really, really, really slow. How slow are they? Okay, so you're looking at things that might be running at hundreds of kips. Hundreds of thousands of instructions per second. The Spec 2006 benchmark suite, and it has not gotten any better since, had instruction counts, dynamic instruction counts in the trillions. If I wanted to run to completion, right, a trillion instructions at 100,000 instructions per second, it's going to be a while, right? So, and as the systems scale up, it gets worse, right? So if I want to look at fully populating a 96 core by 2 threads each, Genoa, HPC system, well, that's not even going to hit 100 kips anymore. Or rather, it'll hit 100 kips, but not 100 kips per core. You see the problem, right? So, and if you want to simulate an actual rack full of 96 core, right? Now you're looking at things that the simulator might not even model terribly well. Yes, Gem 5 actually will model multiple machines talking to each other. It doesn't, it's not great, right? It's not its most well-developed piece of the system. Right? So understanding how things are going to deploy at scale, there are an increasing number of questions where on the one hand, you can only realistically answer them by simulation from an economic perspective, but from a actually simulating everything perspective, very difficult to get a good model. So if I want to understand, for instance, what can I do in hardware to optimize function as a service deployments, like Lambda within Amazon, well, I can look at what happens on one node when I run Lambda functions on it, and then have some analytical model that allows me to try to scale up, throw some queuing theory at it and call it a day. Right? I can't actually model an actual deployment, right? Unless I actually am in fact Amazon, right? So anyway, so you'll just get a tiny little taste of starting to look at a very, very small design space with some fairly clear winners, right? We're just sweeping different branch predictors. Even there, you'll see that different branch predictors do have some different sensitivities across benchmarks. And that will, again, help you get you some insights into the final actual design space project where you're looking at a larger design space on top of simple scalar, where you'll be driving the exploration. Here, the exploration is brute force. We just evaluate all of them. Our design space is small. And so that'll be posted reasonably shortly. So again, my apologies for the delay there. That's I'm going to keep blaming ABET. At some point, it's really me, but I'm going to keep blaming ABET anyway. But yeah, so project 1, project 2. So again, project 1, you're looking at scheduling one tiny little piece of this. Project 2, you're looking at some cache modeling where you can parameterize some caches and model them. So bits and pieces. Do read the simple scalar documentation in your copious free time, right? I won't say it makes good airplane reading if you're going somewhere for spring break. But when you get around to it. I will catch you all on Thursday. Take care.